Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to talk a little bit more about the idea of linearly dependent sets, and here we are going to have a look from a slightly different angle. Okay, so for the first theorem stated here is we have a set of vectors, and this set of vector is linearly dependent if and only if at least one of the vector can be expressed as a linear combination of the others. Well, basically it means that if you have vector 1, vector 2, vector k, and this is just a set of vectors, is it possible that you may express vector 1 in terms of other vectors? For example, C2 vector 2, remember this is the scalar right next to our vector. Maybe C3 vector 3, and then it goes on until the kth vectors. Okay, so is it possible? Can we do that? And notice that here it says at least one of the vectors, so it could be more than a possible combination. So this could be the first possible combination, but it could be a different combination where maybe you have vector 3 right here to be expressed in terms of the combination of vector 1, vector 2, and so on until vector k. So this could be another possible combination. Again, because here we have the keyword saying that at least one of the vector here can be expressed as a linear combination of the rest of the vectors. Okay, well, so that's the idea. Therefore, this specific example here is going to look at how you can show that one of the vector here can be written as a linear combination of the other two vectors. So here we have three vectors. Therefore, logically speaking, we can imagine that it is possible, for example, we could have vector 1 expressed in terms of vector 2 and vector 3. This could be a possible combination. We don't know for sure. It could also be vector 2 expressed in terms of linear combination of vector 1 and vector 3. Or it could be vector 3 that can be expressed in terms of the linear combination of vector 1 and vector 2. So here we have three vectors, and we could have three possible combinations which we don't know yet, and we can't really show at this point of time. So in order to study what sort of vector that can be expressed in terms of the other two, we can have our starting point by considering this process here. We can say that, well, there is a scalar right next to 1, 1, negative 2. That is our first vector. And then we can have the next one. This is also scalar. So we have 2, 5, negative 1. And then this is also another one. This is scalar. 0, 1, 1. And here is vector 0. So this is a system of this is a homogeneous system of linear equations, yeah. And what is the simple reason behind the choice of constructing this sort of equation? Well, to be simply put, I'm sure you understand the idea of, let's say if you have a plus b plus c is equal to 0, then it will be easier to manipulate. For example, it's easier to say that a, or it is easier to express a in terms of B and C. So here is A in terms of B and C. Or you can also think about expressing, for example, C in terms of A and B. And this is what we are looking for in the context of having this set of vectors here. We are looking to try to express vector 1 in terms of, for example, vector 2 or vector 3. This could be one possible example. We don't know yet, and that's what we're going to do. Yeah. So therefore, having 0 here is perfect, because then we can have, or we can express 1 in terms of the other two. So that's the idea. Okay, so that's why we have 0 vector here, because then we can sort of manipulate this situation by having one vector on one side, on the left hand side, and the other two vectors on the right hand side. I hope you get what I'm trying to say here. Okay, so therefore, in order to express something as a linear combination of the other vectors, we need to be able to find the values for all these scalars. Okay, and we already know how to do that. So what we have to do is we're going to express this thing here in terms of augmented matrix. So here we have 1, 1, negative 2, 2, 5, negative 1, 0, 1, 1. Here is 0, 0, 0. And well, I think what I'm going to do next is I'm just going to change this part to be 0. So therefore, I will consider this process R2 plus negative 1 R1. Here we have 1, 2, 0, 0. So here 1 minus 1 is 0. 5 minus 2 is 3. And then 1 minus 0 is 1. And here 0 minus 0 is 0. Also, I'm going to change this part to be 0 as well, and I'm going to do this process on the same stage right now. So I have R3 plus 2 R1. Therefore, negative 2 plus 2 will be 0. Negative 1 plus 4 is 3. 1 plus 0, this is just 1, so here is 0. Okay, next what I can see, or what I can do is well, you can see that this row here is exactly equal to this part here. So if I want to let this equal to be 0, then you will see that the whole part here is going to be all 0. Okay, so first let's change this to be 0. Well, then it will be R3 plus negative 1 R2. Okay, so this is a process that I have to consider. 0, 3, 1, 0. So therefore 0 minus 0, 0. 3 minus 3, 0. 1 minus 1 is 0, 0 minus 0, 0. And this part here will be changed to 1. So I will multiply the second row with 1 over 3. And this is the final look of my augmented matrix. 0, 1, 1 over 3, 0, 0, 0, 0, 0. Okay, so based on this, we can see that this part here refers to having 0 times A plus 1 times B plus C times 1 over 3 is equal to 0. Therefore, B is equal to negative C 1 over 3. And you can see that here we have two equations to be considered, and we have 3 unknowns. Therefore, that should give you an indication that one of the variable here, or the unknown here, is going to be considered as a free variable. So therefore, what we can do is I'm going to let C be any value, any real number. So C is equal to T, where T is any real number. So that is the value of C. Because of that, B is just going to be equal to negative T over 3, negative C 1 over 3, which is equal to negative T over 3. Yeah. Okay, next is this part here. This one basically says that, well, let me just erase this part. So for this one here, it basically says that we have A times 1 plus 2 times B plus 0 times C is equal to 0. So we have A plus 2B is 0. Therefore, A is equal to negative 2B. So here we have A is negative 2 times B, which is negative 2 negative T over 3. And that becomes 2T over 3. So this is the value of A, B, and C, the solution of A, B, and C. Clearly, if you let, for example, T equals to 3, okay, so let T equals to 3. If T is equals to 3, therefore, the value of C is 3, the value of B is negative 1, so negative 1, and the value of A is going to be equals to 2. Now, what makes we choose T equals to 3? Apart from, it looks easier to compute because here we have 1 over 3, 1 over 3. Therefore, if you choose T equals to 3, you can easily cancel out and get some nice number, for example, negative 1 and 2. That is one way of looking at it. But I think the most important thing why T is chosen to be equals to 3 is because then we'll be able to get this constant here, or this scalar here, sorry, equals to negative 1 or positive 1. Okay, sorry, why is it negative 1? Because remember what I told you about this part here. We would like to be able to express one of this in terms of the other two. So for example, we would like to be able to express, for example, vector 2 in terms of vector 1 and vector 3, or vector 3 in terms of vector 1 and vector 2. Therefore, in order to do that, notice that the constant here, or the scalar value here, has to be equal to 1, because then only it will be able to look like this. Okay, so here if you see all the values given here, we can then write this part here. So this part here will become, okay, so it will become 2 1 1 negative 2 plus negative 1. This is 2 5 negative 1, and then plus 3 0 0 1, sorry, 0 1 1, and this is equal to vector 0. So notice here, this is negative 1. Therefore, we can then consider having this on this side. So it becomes 2 1 1 negative 2 plus 3 0 1 1 0 0 0 plus 1 2 5 negative 1. And 0 vector, when you add with another vector, it will get this vector. Okay, so we can write it in terms of, therefore we have 2 5 negative 1 is equal to 2 1, 1, negative 2, plus 3, 0, 1, 1. And here is the second vector expressed in terms of the first vector and the third vector. Okay, so this is an example of linear combination where you have managed to show that one of the vectors here can be written as linear combination of the other two. Okay, right. Next is we're going to move on to this theorem here, which is in essence it talks about the same idea of linearly dependent sets, which I have already explained in the first part of this story, of this whole story about linearly independent or linearly dependent. But this is expressed in a slightly different way. So basically it says here that you have vectors v1, v2 up to vm. So now we have up to m vectors. It doesn't matter. It's just an alphabet here. M is just an alphabet to represent, well, how many vectors you have. So these are column vectors in Rn. So here we have dimension of n, so real number, the dimension is n, and let A be the n times m matrix. So with these vectors as its column, so these vectors here becomes the column, so it becomes A matrix. And then it says here all the vectors here are linearly dependent if and only if the homogeneous linear system with augmented matrix here has a non-trivial solution. Now this has already been explained, like I said just now, in the previous video. So this is just another way of saying the same thing basically, okay? Well, what it means by the whole sentences here is that imagine you have vector 1, which can be written as a column vector. That means you can imagine there is the first component, second component, and then you have up to nth component. So this is first, second, up to nth component, because here we have the dimension of that is n, okay? And then vector 2 is also the same thing. You have like first component, second component, and then the nth component. And you have more vectors up to m vectors. So m vectors is the same thing. You have first component, second component, and then here is the nth component. So if you combine all these vectors together, so you combine all the vectors together, imagine you combine, this is the first vector, and then this is the second vector, and then this is the last vector, then this thing here becomes a matrix, and we call this matrix A. So this matrix A is n times m matrix. Why? Because here we have n row, the number of rows here is n, and up here is the number of vectors. We have m vectors. And when you consider the combination of all these vectors with 0 here, so that indicates a homogeneous linear system. So basically you are then going to combine all these values here. So here is matrix A, and then this is 0 vector on this side. And if you have a non-trivial solution, so you go on and use ERO, elementary row operations, and at the end of the day you get non-trivial solution. What is the meaning of a non-trivial solution? It means that at least one of the solution is non-zero, and I've talked about the idea of non-trivial solution in the previous video as well. So if you are not sure what it is, please go and study the first part of this section on linearly dependent and linearly independent sets, okay? So when you have this matrix and you get a non-trivial solution, that means the set of vectors here is linearly dependent. So that is just another way of saying the same thing that I have already talked about in a slightly different way. That's all, okay? Right. This is the standard unit vectors. What it means by standard unit vectors is just if you have the first vector here, so if this is the first vector, then we have value 1 designated at the first component and the rest will be 0. If this is the second vector, then 1 here will be assigned at the second position here. It is the second component with value 1 and the rest are all 0. And similarly, if this is a third vector, therefore 1 will appear here and the rest are all 0. So it says here that all these vectors are linearly independent. Why is it linearly independent? Because, well, first of all, in order to know whether it is linearly independent or dependent, this will be your starting point. You need to consider coming up with this sort of equation, and then you need to be able to find what are the values of these scalars. And in order to solve this homogeneous system of linear equations, what you need to do is you can represent everything here in augmented matrix, so it will look like this. And because this matrix is already in its simplified form, this is actually RREF. Therefore, clearly you can see here for this part here, C3 is equal to 0. For this one here is C2 is equal to 0. And here is C1 equals to 0. So what we have here is a trivial solution where everything is 0. And because of that, we say that this set of vectors here is independent. Okay, right. So this is another theorem that says if you have a set of m vectors where it comes from a vector space of real number with n dimension, this set of vectors here is linearly dependent if m is greater than n. So that means m here is the number of vectors that you have in the particular set, and here is the component of that vector, component or dimension. Okay, so as an example here, this is an augmented matrix in terms of A and vector 0. So clearly, in order to get this matrix here, actually it comes from the process of having vector 1 and 2, this part. So here we have some scalar plus another scalar. Here we have 4 and 1. This is a second vector, plus C3. This is the third vector, is equal to vector 0. So here clearly we have 3 vectors, but then we only have 2 dimension or 2 components, and because of that, if you try and solve this matrix, you apply all the elementary row operations, you might get the situation where you are left with either 2 equations to be considered, or you might have 1 equation to be considered. And that is because it is possible that you might get all this part here equals to 0. So when it is equal to 0, you only have 1 equation to be considered, right? So that those 2 here are the possible scenarios. And because of that, since you have like a less number of equations to be considered, but you have like 3 unknowns to be solved, therefore we can expect that one of these variable here will be considered as what we call this free variable, so it can take any value. And because of that, clearly the system here has at least one non-zero solution. You have a lot of possible solution in this case, and therefore we will say that the set of vectors here will be linearly dependent. Okay, I think that's all for now. Thank you very much for watching.